Hello, can you hear me? Yeah, I think the sound is okay on my end. Thanks a lot. Thanks. All right. Thanks for joining the stream, first of all. Um, your support is much appreciated. Last week's stream went very well. My goodness, I couldn't believe how well it went. I think um, because usually not a lot of people watch stream recording, but that video, the recording is like a 3 hour recording, has gotten like over 5,000 views over the course of the last week, which is kind of insane. And I didn't even talk about anything in my opinion, earth shattering. So and the thumbnail design is pretty average. It's just the cover of a book I'm using. So I was really pleasantly surprised. So thank you very much. Before we actually go into the math, would you like would you guys like to talk about just like to chat, right? I mean, it's a pretty casual format. Um, for example, where are you guys from? And I'm from Canada, by the way. And well, I'm not from here. I live here. I was not born here. But this is where I live and where I work. Do you guys, anybody want to say something in chat? Where you guys come from? What makes you interested in math? Things like that. But I'm just like to react to the responses I've been getting so far. Right now, the I would say a lot of people are giving very positive feedbacks to the stochastic calculus series. Two episodes are out, by the way, and definitely this is I'm studying economics and statistics at Laurier. Are you in Laurier? My goodness, I'm from Waterloo. Yeah, I am Chinese. I'm ethnically Chinese, and I was born in China. I was born and raised in China. Yeah, that's my background. I'll say more about myself in a Q&A video. Um, so, yeah, it's great to know. Um, where was I? I was saying I'm from Poland, just finished studying accounting and finance in UK. We're doing quant finance. Ah, well, good luck then. This is really exciting, quant finance. And I'm working on a book recommendation video on stochastic calculus as the companion, obviously, to the stochastic calculus series. And there's going to be books that are particularly suited for quant finance. Um, so I will give a rather comprehensive, if I do say so myself, list of books. Thank you so much. And actually, Beru, stop calling me Dr. Ming because I'm not a doctor. Okay, I only have a master's degree in applied mathematics. But thank you so much. Thank you so much. A lot of people call me professors and doctor. I am neither of those. Okay, but I mean, I'm just a person who likes math, and I try my best to share my own understanding of math, and I'm just glad that a lot of people found that helpful and resonating with them. Okay, but yeah, where I was talking about the book recommendation. So I would, because I'm working on a book recommendation video on stochastic calculus because this is such a big topic, right? The series is only meant to get an absolute beginner into the subject. Okay, an absolute beginner for that series refers to someone who knows basic probability, non-measure theoretic probability. Okay, knows how to take expectations and variances, for example, and knows the basics of calculus. Okay, the basics of meaning a computation based, okay, not proof based, a computation based sequence of calc 1 to calc 3. Okay, so that's the idea. Calc 3 typically finishes somewhere around multiple integrals, like that. Right? Calc 3 is typically multivariable calculus. You do things like partial derivatives and multiple integrals, and perhaps sometimes, depending on the institution, there's also vector calculus and perhaps Fourier series. Okay, but that's kind of the intended audience of that series. So it is my belief that one can obtain a working knowledge, like on the level of manipulation, okay, and the intuition, so to say, of the subject, like the spirit of the subject. What is this about? Okay, without being bogged down into the technical proofs. Okay, because traditionally the barrier of entry, in my experience of this field, is rather high. So, Dan Wu, I don't know about your exact mathematical training, but you said you studied accounting and finance in the UK and are doing quant finance. So, typically in North America, so I'm just talking about an average person with a similar background in North America. This is a very, of course, this is a lot of people's fields of interest, right? But stochastic calculus, as is usually presented, has a very heavy mathematical barrier of entry, right? So you gotta know real analysis and preferably some functional analysis, and also measure theory, which is you can call that advanced real analysis. So you can understand measure theoretic probability. And measure theoretic probability is usually, in the math department at least, the prerequisite for studying stochastic calculus. And that's a lot, right? That's needless to say, that's a lot. And people sort of say start a quant finance program without such a background. Reading the original tech is going to have a hard time. Your mileage may vary. I'm just making predictions. Reading the classical treatment on stochastic calculus, which is entirely normal, and because the course workload, so to say, in such programs are pretty heavy, right? You typically don't have the luxury of, for example, starting from baby rooted and starting from real analysis, measure theory. Of course, you will encounter those things, and it's that those things are still important. But sometimes you get so bogged down that you don't see the main intuition of the subject, and which is, in my opinion, really a shame. Stochastic calculus is a really fantastic topic, and it's got so many areas of applications: finance, physics, engineering, and even social science. Right. So it's really a fantastic topic, and the intuition of it is really not that complicated. And this is something I would try. I've been trying to emphasize on in my videos. Okay. Of course, there's going to be some hand waving, and I do admit so, frankly, whenever I do so. Okay. I will say very plainly, this is a heuristics, this is not a proof. But I would just try to give enough steps so that at least intuitively it makes sense. It's kind of like teaching high school kids. No, not kids. Sorry about that. I know I have high school followers. Teaching high school students calculus, right? You don't start with the least upper bound principle, even though that's the logical starting point. Okay, you don't start with the completeness axiom of the real, right? Instead you draw a graph and say, okay, this is the secant line, and if you put the two intersections closer and closer to each other, you get the tangent, right? And here's the average speed. If you shrink the time interval to 0, you get the instantaneous speed. Things like that, right? and you can work with those tools quite proficiently, right? And typically what is called for in applied fields. I'm not saying like advanced materials and rigorous proofs are useless in applied fields, not at all, because we want to know the limitations of our tools. That's also quite important, and that's something because I mean, Beast from the East, thank you so much. I'm putting like the fundamentals in the form of quizzes, sometimes summaries. Perhaps I've not been doing enough of them recently, and also live stream. So anyway, back to stochastic calculus. So the next video, I'm still thinking about what would be the next appropriate topic. So stay tuned. Okay. Anyway, so that's the stochastic calculus series. What else did I do this week? I made a video. Are you Chinese? I'm visiting. Oh, sorry. I already answered that question. Yes, I am Chinese. I'm more of my real analysis class, which explain the motivation behind why stuff like the suprema and infima and more. Yeah, that's interesting, and it's definitely worth discussing. You can think of suprema and infima as generalized maximum and minimum, because maximum and minimum don't always exist. That's obvious, right? But we construct the real numbers in such a way that if a set is bounded, supremum and infimum always exist. So that's a nice mathematical property to have. Okay, and once you have the real set of real numbers that satisfies what I just mentioned, basically the least upper bound property, you can construct calculus from scratch. So, so what I mean, this is it seems like this is I'm trying to communicate. What I'm trying to communicate is a very natural trajectory in any science, right? Not just math, but physics, biology. You first observe phenomena. Okay, this is something you always do. You start from isolated phenomena, and then you try to understand the phenomena. Okay, and to do so, you develop tools. Right? And once these tools are developed, we're starting to look for the connections between them. Because, for example, throughout the history of mathematics, the problem of area is an old one, right? Since ancient time, people have been trying to calculate areas of different forms. Those things existed since antiquity. And people also are interested in tangents, right? Tangents. But it was only until early modern time, that the connection between those two problems are discovered, aka the fundamental theorem of calculus. Right? So we observe phenomena, and then we try to come up with tools to understand those phenomena. And once we have enough tools, we start to look for their connections, and that's called a theory. Right? And the thing is, we wish to, and there's more. We wish to know the limitation of our tools, and to in what extent can they be extended, right? To in what area can they be extended? Because calculus is so powerful, we want to transfer our knowledge to less familiar fields, right? Less familiar areas. For example, we want to differentiate more complex objects. Okay, can you differentiate, say, a matrix? Can you do that? Of course, we would like to do those things, right? So we would like to see how far our familiar tools can be extended in new settings, right? And to do so, we require a firm foundation. And by that, we typically, in math at least, we wish to come up with a small set of unifying principles so that everything else can be derived from it. That's the axiomatic mathematics. So the history of mathematics sort of developed this way, right? Well, in a way I just mentioned. And along the way, notions like supremum and infimum were invented so that we have a secure foundation. And even to this day, there's a minority of mathematicians who have suspicion towards this foundation, and which is, I think, a healthy phenomenon, right? So that's more of a high-level motivation, not a technical motivation, right? And so back to what we do on the channel. So far, the videos, especially the recent ones I've been making, tend to aim at people who have a background in basic calculus, as I said, and maybe probability, and also I kind of assume linear algebra too, and linear algebra as well. And I got requests on how to secure those fundamentals and whether I would make series about those things. But for now, I don't think I can make like a dedicated calculus series. I'm not going to teach you calculus from scratch. This is, I'm not, I mean, never say never, right? But it's not currently on the to-do list right now. There's a couple of reasons for that. First, I think there's, in my opinion at least, that those materials are already pretty saturated, right? They're kind of done to death, in my opinion. I mean, of course, if you're new to the subject, that's not done to death to you. But I'm just thinking there are so many good calculus courses, linear algebra courses already on YouTube alone, right? Then it's really hard for me to contribute anything more valuable, right? There's already so many other creators, amazing creators who have fantastic material on those things. It's hard for me to. I'm trying to fill like a niche and a gap, and those areas are difficult for me to develop the channel. I mean, I'm a YouTuber after all. As I said in one of my videos, I'm greedy for views, right? So, I'll be candid about that. What's up, math nerds? Oh, hi. Yeah. So, but I do provide daily quizzes on those fundamentals. So I set a range of topics that I make quizzes from: calculus, linear algebra, basic analysis, and basic real analysis, as well as basic probability. That's kind of the areas I'm looking for problems, and most of the problems are in the quizzes I made myself. Okay, and if something that is taken from a book, I'll put the reference there. So the idea is to have a low-stake environment for people to practice some of the easily confused or missed topics in those areas, and it's sometimes a good reminder for me, at least, in my career and my learning path, is that sometimes I thought I understand something, but then I do a problem, it reveals the cracks in my foundation. Right? So I'm guessing everybody has those experience, right? You thought you understood calculus until you see a problem that you got wrong, right? Which I think it can be a fun experience. So the idea is to have a low stake environment for practicing those things, and also do live streams. So for example, right now I mean, even though this is called advanced calculus, we're doing abstract linear algebra, right? Which I think is a good point. It's a good topic to start because advanced linear algebra or abstract linear algebra does not so to say, is the level of abstraction from calculation-based linear algebra to advanced linear algebra is less than the level of abstraction from calculus to real analysis, if you know what I mean. So that's my personal experience, and I think the habit, okay, the habit of using abstract linear algebra as one's active mathematical vocabulary is a vital skill in both pure and applied mathematics. So I want you to think about a problem in terms of them. Okay, it's not like if you're asked about what is the property of a vector field, vector space. Gives you a space and it asks you to calculate the basis, calculate one basis, find the dimensions, do the Gram-Schmidt, all those stuff. Okay, these are passive knowledge. These are passive knowledge. What I aim and what I recommend everyone following this channel is that you use the language of abstract algebra. Sorry, not abstract algebra, abstract linear algebra as part of your active mathematical vocabulary. When you see a problem, when you approach a subject, you naturally think about things in terms of that, right? So that's the idea. So you want to, for example, if you're taking differential equations, and you want to think about differential equation in terms of, well, the operations in vector spaces. Okay, so that's the natural next step. Once you develop this habit of looking at mathematical subjects through the lens of abstract linear algebra, it will help you a lot. Right? So that's why I choose this topic. Question: did you see? I did see your post on the result of the last problem. Sadly, the correct answers were marked green. I didn't get a chance to truly take the quiz. Is there a way to prevent this? Well, those are old questions. Those were very old questions. I mean, not very old, like a month old. Right? If you want to try those questions yourself, just go to my community tab, and you can do those questions. So yeah. So there's that. I mean, it's not that big of a deal if you see the correct answer. The answers themselves don't really matter that much. Okay. The idea is using those questions to see whether there's a crack or hole or a missing piece in the foundation, right? So I don't actually mind if you look at the solutions, and as long as you're being honest with yourself. That's the most important part, right? So this is of course, I mean, as I said, this is a low stake environment, right? And as long as you're being honest with yourself, making an effort, and I think that's already more than what I hope for from these quizzes. Why do you think this? Why do you think this? Think what? Why do you do this? Oh, why do you do this? You mean do this YouTube channel? Well, I like math. That's as simple as that. Okay, and I wish to share my experience and some understanding of math with some people, with like-minded people. That's about it. Okay. Unless you have some specific activity that I do which you are not sure why I'm doing them about. Okay, so that's anyway. Where was I? I think. Oh, actually, there's something else I would like to mention because a lot of people ask me about where did you get this understanding of statistics in terms of geometry, right? And to be honest, actually, just as a self-promotion, I did a few videos recently, but on the statistic of geometry. Sorry, not the statistic. Yeah, the geometry of statistics. But it seems like more people are interested in the stochastic calculus stuff, so I might have to prioritize that. Okay, but I'm not abandoning mathematical statistics. Okay, of course not. It will be a staple of the channel. It's just in the short term, I'll be prioritizing on the stochastic calculus part. But anyway, back to the geometry of statistics. It rather amazes me that such a treatment is not mainstream. Okay, but because if I look at my standard textbooks, okay, this is not my standard textbook, but the rather standard textbooks in the field, probability and statistics, at an introductory or intermediate level, most of them do not take geometry or even linear algebra. Okay, when we say the word geometry on this channel so far, we mostly refer to the geometry of vectors. Which is, in my opinion, really a shame. I don't have, the answer is rather depressing. I don't have a single text or just a few candidates that recommend this kind of perspective. But there is this book, which I learn a lot from. Okay, so hang on, let me find the name for you. I mentioned a couple of times on the channel. I can think of the top three, and I'll list them here. Giving a shout out to these books. Okay, and that's the first one. The first one is called Weighing the Odds by David Williams. Okay, this one is a rather, I would say, elementary take on the subject. But don't mistake elementary as simple. Okay, when we talk about, the number theories have this phrase elementary as well. Right? If you have any, do we have any number theory guy here? So when a number theory guy says elementary number theory, he refers to the part of number theory that does not require complex analysis or abstract algebra. Okay, not algebraic number theory, not analytic number theory, but just elementary number theory. So there's a technical meaning for that. Okay, that's kind of the same way I'm using the word elementary. So this book is elementary in the sense that it does not use measure theory or real analysis. Okay, it does not. I don't think it assumes any real analysis at all. But don't mistake that as easy, because the ideas and exercises are quite deep. Okay. So check this one out. I mean, the book is ridiculously expensive. Unfortunate reality in the world of publishing, but nothing I can do about that. If you have access to a library, that would be great. Okay, go check out this book, Weighing the Odds. That's the first recommendation. And the second one is called the Hilbert space method in probability and statistical inference. So this one is definitely a graduate level book. It assumes I would say a modest familiarity with basic real analysis. It does not assume you know Hilbert space. Okay, it does not assume you know Hilbert space. And by the way, the first author is a professor in my university. This book, Hilbert space method and probability and statistical inference, really got me into thinking about probability and statistics in terms of L2 geometry. Okay, thinking of random variables as vectors. Okay, and draw a lot of diagrams to visualize as many formulas as possible. Okay, and the book is still at a higher level compared to what we do on the channel. Don't get me wrong. Okay, I'm not following this book. I'm just using the analytic tools provided in this framework, the Hilbert space framework, to recast some of the basics. Okay, so that's the idea. So this book is also a good one. Also, this is insanely expensive. I don't know why these books cost like over $200 freaking dollars. It's crazy. And what else? And I think there is another book which I'm struggling with the name right now. It's called. I think it's. Hang on, let me find that somewhere. Do I? In my search result. I'm trying to find it in my search result. All right. Is it called Mike? Is a guy named Michael Eaton or Morris Eaton? Yeah, Morris Eaton. Morris Eaton, multivariable. It's called multivariate statistics. Hang on. The vector space approach. Yeah, this is a book. There you go. That's another book name. So this one does the classical statistics, like the linear model stuff, and multivariate analysis in the form of abstract in the setting of abstract vector spaces, okay, not Rn. And don't uh, and what I'm trying to say, the book is tough. Don't get me wrong. This book is very tough. Perhaps the toughest among all three. So that's why I'm putting things in that order. Weighing the odds is the most elementary one, and perhaps most readable one. And actually, is not in readable in the sense that's easy, but the you can certainly feel there's a persona. There's a persona, okay, a personality behind the voice of the author. So that's very nice. And the next up is probably the Hilbert space method. This also connects a lot of the modern frontier of the subject, which I like. And the last book is a complete treatment, is a complete geometric treatment of the classical statistics, the linear model stuff. Okay, but don't be fooled by sort of say the limited scope. It only treats things like linear model. You will think, oh, that's easy. I know linear model. I know linear regression. But the treatment, the level of treatment is very high. Okay, and I think like in some of the later chapters, it also using like group theory, topology, Haar measure, which is a lot. Okay, which is a lot, but it's certainly the most geometric of all among all three. The most geometric among all three. But what makes me rather sad is that a lot of the geometric treatment, the books, I mean, they don't have many pictures. Okay, so you kind of have to read the notations and translate those translate those notations into a picture yourself. I mean, it's a good exercise. Don't get me wrong, but I'm just saying that it can introduce a lot of unnecessary difficulty, in my opinion. Like, why can't you just draw a picture in the text? Like some of my favorite authors, even pure mathematicians, they have pictures in the text. Like, you know, if you guys know, there's this author called Michael Spivak. His book on calculus are considered as classics. His books are super rigorous and they have pictures. Right? And I don't know why. I mean, the book by Eden is a fantastic book. I just wish there were more pictures. Anyway, so, and regarding pictures, the basic philosophy of this channel, when it comes to the visual part, right? A lot of people complimented me, thank you very much, for bringing geometric intuition. And I have a self-imposed technical limitation, a technical constraint I put myself, is that the visualization tools that I use for my videos are limited to PowerPoint, Desmos, and GeoGebra. Okay, and no graphics engines is allowed. I put those constraints on myself because why do I do that? It's kind of an anti 3 blue 1 brown, if you know what I mean. I mean, of course, I fully respect 3 blue 1 brown's work. I mean, he's a genius. Like, his works is a work of genius. His videos, his videos are the mass equivalent of Hollywood blockbusters. Okay, these are marvel pieces of art and engineering. But I'm trying to do something different on the channel. I'm trying to show that the beauty of math is independent of a graphics engine. The beauty of math is in the logic itself, the interplay between intuition and rigor, the interplay between abstraction and concrete applications. And you're not just marvel at its beauty, and instead you're an active participant. I firmly believe what Paul Holmes' words, mathematics is not a spectator sport. And I was worried about if I use these fancy graphics engines, would that inadvertently give an impression, a false impression, that in order to have visual intuitions, you have to be a software engineer. No, you don't. Archimedes draw in the sand. I think me as a student, one of my biggest regret, and something that I certainly did not do enough, is that I didn't draw enough pictures. I had the impression that, oh, if my pictures does not look nice, I'm kind of embarrassed about my drawings, and that's a terrible mentality. You should always try to draw. You should always try to draw. Like, uh, like what's the cost here? You should always try to draw pictures yourself, however rudimentary, on the back of an envelope. So this technical limitation I do impose on myself. For example, here's what's the slides for my video I posted today. So this is this one. So yeah, so the visuals are like that. So I put the limitation on myself. If something that cannot be implemented with PowerPoint, Desmos, or GeoGebra, I will discard that. So it's a philosophy that kind of gets back to the basics, okay, and using the visuals as a bridge and not as an art. Okay, these visuals aren't an art. These visuals are bridged towards rigorous proofs, and that's a means to an end. Okay, it's perfectly legitimate to treat mathematical animations as an art in itself. Okay, I'm not saying that's something illegal. Okay, but my goal is to use visualizations as a goal, as a bridge to approach seemingly impenetrable subjects. Okay, I kind of rambled long enough. Let's do some actual math. And I haven't looked through the chat for a while, and I was just keep talking myself. Let me see some of the responses. I like controlling AI, but it makes me feel like I need a master's degree. Well, you can certainly study math without a master's degree, I would say. And controls and AI certainly do call for a lot of advanced mathematics. So, and it's certainly possible to learn advanced mathematics without a master's degree. I would say, yeah, YouTube channel. I like your stuff, by the way, working through the stochastic calculus theory and self-studying foundation. Thank you so much. Speaking of multivariate, wondering what book do you recommend for multivariate real analysis? Okay, so I was talking about multivariate statistics, right? If you're talking about multivariate real analysis, there's a fantastic book. There's an absolutely amazing book, which I think don't get enough attention. It's called Functions of Several Variable by Fleming. This one right here. Okay, so if I'm ever going to make like the fundamental videos, so linear algebra, calculus, like basic probabilities, those sort of stuff, I think this book will be my go-to choice for multivariate real analysis. It's approachable enough. Okay, it's approachable enough, but still completely rigorous. And it has plenty of exercises. I do have a physical copy of this book. It's a fantastic book. So if you look at the cover, that's a what's that? That's the what's it called? The modern Stokes theorem, generalized Stokes theorem. So this is pretty amazing. Okay, so yeah, definitely go check this book out. What else? Another book that's also quite nice is by Moncrief. What's the name? Huh. I think it's, by Moncrief, the famous topologist. Analysis on Manifolds by Moncrief. So yeah, if you're preparing, so you're doing multivariate real analysis, I assume you want to do differential geometry and topology, right? So, so yeah, why don't you start from analysis on manifold? Yeah, this one right here. Analysis on manifold, that's the cover, alpha and omega by Moncrief. So that's a very nice choice. I think at the same level as Fleming's book, but Fleming's book has more applied favor to it, which is the reason I prefer it. Okay, um, so it in the book that if in the Fleming, I mean he's I think he does both pure and applied mathematics. Perhaps that's the style of his expedition. By the way, Fleming also wrote books on a stochastic control theory, and also he does, I think, geometric analysis. Very formidable subjects. So one is considered bona fide applied mathematics, but geometric analysis is like highly abstract pure mathematics, right? So that's why perhaps I like his book a little bit better than Analysis on Manifold by Moncrief. And of course, how can I forget Calculus on Manifolds by Spivak? Right? So actually, this is the book. This is the YouTube video. My goodness.
I have been asked by more than one, being the number 2,
Right. So
of my
that's
wonderful
the that's
subscribers
the kind
to
of I don't want to play the video here, but yeah, that's the book. So Calculus on Manifold by Spivak. But this book is very terse. It's not great for self-study. The proofs are very beautiful for sure, but if you're a self-learner, I think you would likely not have a great time with Spivak. It's like grinding through baby root in yourself. Okay, so yeah, if you want, my recommendations are multivariate real analysis, perhaps with the aim of getting into differential geometry and topology. Certainly go check out Functions of Several Variables by Fleming and Analysis on Manifolds by Moncrief. What about Calculus Early Trends? That's Stewart, right? That's Stewart's book is I wouldn't say it's a good first introduction. It's a good book for handling the foundation. It has very nice, sort of approachable exercises. Approachable. If you're using the book, the Calculus Early Transcendentals, as a first introduction to the subject, there's absolutely nothing wrong with that, and it's rigorous enough for that. Okay. It supplies enough proof that does not intimidate a beginner, and which I think is a good thing. You do want to develop confidence in the subject, but you certainly need something more if you wish to get into some of the upper division undergraduate or graduate level. I mean, I used Calculus Early Transcendentals. A lot of people seemingly a little bit. I wouldn't use the word like critical, but a lot of people seem to criticize Stewart's book a lot. But you got to know, like, what is this book meant for? I think it does a great job for what it's intended to do. And my only complaint is the price. It's kind of ridiculous how many new editions it pumps out. That's my only complaint, and every edition seems to be getting ever more expensive. That's my only complaint. But the content of the book is pretty good. You can learn a lot of math, a lot of calculus from Calculus Early Transcendental. The definitions there are satisfactory, rigorous. Okay, and it's got proof in the appendix. So if you do want to know those proofs, you can put in the appendix. Also, perhaps another complaint about Calculus Early Transcendental is that it has no bibliography. I don't know about the latest edition, but the edition I use has no reference list. Okay, so a beginner would not have an idea, a very clear picture of what he or she needs if he wants to if he or she wants to dig deeper. What's the next step? Because calculus is a big subject, and it's not realistic to expect any one textbook to cover the entire full picture, right? So um, I'm amazed how math enthusiasts are so simple. Do you mean me? Um, if so, I'm yeah, I guess um, in a way I am a simple person, you know, but, and I take that as a compliment in the sense of no fluff, I guess. All right, enough rambling. Let's do some actual math. My goodness, let's do. Why don't we begin with a question? This way, you're more likely to be active in our stream, which is something I want. So, where did we finish or end up last time? I think we were talking about vector space and subspaces, right? Abstract vector space and subspaces. And we were in the exercise department. I think it's still a little bit earlier. So yeah, by the way, this book is Advanced Calculus by Loomis and Sternberg. Should I share the link once again? Loomis and Sternberg. This book is available for free, okay? That's why I'm using this book. What's that? It's what is it called? Public domain or open domain? Yeah, public domain material. So I don't get into trouble with the publishers. Sternberg books. So yeah, this is the old Harvard 55 textbook. Harvard 55, if you guys know, it's sometimes considered one of the hardest math class in the world. Well, certainly in North America. So this is this book, Advanced Calculus. Okay, just search books of Shlomo Sternberg, Harvard mathematician. Rest in peace. And this is the book, Advanced Calculus. So there we go. Without further ado, let's look at one of the exercises from section 1. And actually, I should put out a repository of some sort. I'll figure that one out. Maybe GitHub, and put my notes and slides on there, because I've been getting emails and comments of like the copies of my notes, the videos and stuff. Hi Ming, moving love from Italy. Your videos are truly great. Thank you so much, Michelle. It's pretty late in Italy, right? I don't know. Like, I think UK is 6 hours ahead. It's like pretty late in Italy. You're dedicated. Thank you so much. Where's exercises? All right. I think we're close. Still not close. Fundamental notions. What is this? Vector spaces, right? We were talking about vector spaces, but not linear maps. We didn't talk about linear maps. Here you go. Let's see. So here, why don't we do an exercise? I just select a random one, whichever one I found interesting. Let's do 1.18. Prove more generally that the intersection W equals to the intersection I in big I, Wi of any family of subspaces of V is a subspace. So the intersection of subspace is still a subspace, and it's arbitrary intersection. And it's a good exercise, because we need to be comfortable with working with arbitrary union, arbitrary intersection, those sort of stuff. Okay. Can I hide this? How can I hide this? I don't need this. Okay, it's a really dumb way, but okay, let's just settle this for now. I think it's enough space for us to work with. So first, let's start with the definition. This is too thick. The definition of intersection, arbitrary intersection. Definition. Yeah, YouTube channel. I like your stuff, by the way. Working through the stochastic. Oh, sorry. I don't know why there's a lag of chat on my OBS. I should. Yeah, math is good. Yeah, so it certainly is one of the greatest things in the world. As I said last time at the end, if you spend your life studying mathematics, you are safe to say you didn't waste your life. The original quote is modified. This is a modified quote by Dostoevsky. Dostoevsky said, if you spend your life studying human nature, you have not wasted your life, or something like that. Anyway, here's the definition for the intersection. Let, say, AI, I in big I, this is too thin, no? If somebody is watching it from a mobile device, that's not very nice. Okay, this is, I think, better. Okay, be a collection of sets. Mathematicians tend to avoid phrases like sets of set. It's just something we don't say. We say family of sets or collection of sets. Okay, which is really no different from sets of sets. It's just a way to avoid sounding repetitive. And I is called an index set, which is arbitrary. Okay, arbitrary. It does not have to be a set of numbers. I is index set. So the definition for arbitrary intersection, AI, is defined as such. Is the elements A in AI for is a elements A in elements A such that there exists a little I in big I, that A is in big I. A is in AI. Okay, that's the definition of. Oh, no, I was talking nonsense. My goodness, this is for all. If it's union, then there exists. Okay, so this is for all, and just as a comparison, let's write the union, arbitrary union. That's the definition of arbitrary union. So this should be part of the material in like an introduction to proof course. Okay, the definition for, actually, you know what? This is a perfect thickness, I think, for a mobile device. I'll just stick to this one. A in AI. Okay, so this is an arbitrary, I can't spell, my God, arbitrary intersection. Just in case somebody is rusty with those notions. The second is arbitrary union. And here we're only using the arbitrary intersection. Okay, so we wish to prove that the arbitrary intersection of subspace is still a subspace. The geometric intuition is rather straightforward. If you have two planes through the origin, right, assuming they're on the same plane, then their intersection will be a line through the origin, which is also a subspace. In the case that they're the same, then the intersection is trivial. It's the original plane. So we wanted to prove this is true for arbitrary intersection. So how do we do that? Well, we use the definition, or I think lemma in the book. Let's use one of the lemmas in the book. So when you do these proofs, it's always a good practice to check if there's anything in the arsenal Okay, the lemmas, the definitions, the theorems, these aren't just boring facts. These are arsenals. These are without these, you're like a soldier without weapon, right? So we can. It's always nice to when you do the exercise, look back, look back, look back, and that's the make that as a habit. So the lemma is W is a non-empty subset of a vector space which is closed under the operation of V. Operation refers to addition and scalar multiplication. So we need to close under addition and close under scalar multiplication. Then W is itself is vector space, and we call that a subspace. So that's a result and a definition together. So our idea is to use this. And in some textbooks, this lemma here is called the subspace test. Subspace test. Okay. So we need to check three things. One is non-empty. Let's call that the zero step. You check a set is non-empty, and typically what you do is you check whether 0 is in W. And next you do checking closeness under addition. Close under addition. That's one. And close under scalar multiplication. Okay. So that's the subspace test, the three steps. All right. So let's do that. Let's change the color to have blue here. All right. 1.18 proof. Let's do that. So let's start with step 0. Checking 0 is in the intersection. And this is certainly true because 0 is in every Wi. Since for all I, Wi is a subspace, which is a vector space. A vector space always contains 0. Zero belongs to Wi for all I. Okay, and I mentioned something in my post, one of my posts, that when we write proof, when we read proof, it's a good mentality, and I would actually argue that's mandatory to use a 2-column method. So this is our deduction, and we need to add a justification for that. What is that? Well, that's the vector space axiom. This is the vector space axiom. A subspace is a vector space, and one of the vector space axiom states that additive identity, aka 0 vector, must exist in every vector space. And that's the reason. You have the deduction and the justification. Okay, and then therefore, by the definition of the intersection, 0 is in I. Not from 1 to n. In big I, Wi. Therefore, so what's the justification for that? That's the definition of arbitrary intersection. Okay, so step 0 done. Step 1. What's step 1? Step 1, we prove addition is closed. Prove addition is closed. So to do so, let's pick 2 elements in the intersection. So let's pick, why don't we pick x and y in the intersection? So when we write this, let something blah blah blah. Okay, this is a common, what's that? A common phrase we use in proof writing. What it really says is, this is an abbreviation. This is an abbreviation of let x and y be arbitrary but now fixed elements in the intersection. So that's what we mean. So this is really just a convenient way to write this sentence. Okay, so now we treat x and y as arbitrary but now fixed. Once we manage to show any property that holds for x and y, we can immediately conclude that the property we just showed works for any pair elements, any pairs of elements. That makes sense. Okay, so there's that. And then let's do the addition. We want to show that x and y need to show another common phrase in proof writing. Okay, so I'm not doing a series, or at least right now, on the basics of proof writing. Okay, I don't have time for that, but I try to demonstrate the basic techniques in live streams. So this is standard proof writing material. Okay, so need to show this. Okay, so what can we say? By the definition of intersection, we have for all I, x is in wi and y is in wi. Right? Right. So that's this is from the assumption. This is from the assumption. So let's write that. This is by the assumption. Okay, second column. All right, so well, what can we say about x plus y? Well, x plus y is in wi. Since wi is a subspace, vector space axioms is a subspace. Okay, and we just show that x plus y belongs to every wi, so x plus y is in the intersection of wi as needed. And that's from the definition of arbitrary intersection. Right. So if you have done any of my quizzes, you might have seen a common format. I mean, not that common, but a few already. Which result depends on what? Right. For example, I made a question this week on whether the Cauchy-Schwarz inequality depend on some of the axioms of inner product. And I made a post about that. And I think that question is very funny because it like each I have 4 options, by the way. Each got like 25%, around 25%. It's very uniformly distributed. Okay. So this tells me that the popularity of the 2-column method is not widely appreciated. Okay. I mean, it's by a sample, of course. The idea is when we do proofs and read proofs, at least mentally we should do this. So this way you can see, okay, what definition, which axiom has a higher appearance and what steps depend on what, right? So here we just show that x plus y is in the intersection, and that's something what we need, right? So when you write need to show and you manage to get that, let's write as needed. It's like in coding you have a bracket as you close it. All right, so this is good style, if I do say so myself. I mean, it's nothing boastful, okay? It's just standard proof writing. So anyway, second, you have scalar multiplication is closed. We also need to verify that. And the proof is very similar. Let x be in the intersection of wi. C be real. Right? In this book, the vector spaces are assumed to be real vector spaces unless specified otherwise. Okay? Need to show C of x, C of C times x is in the intersection. And let me know if my writing is too chicken scratch like. Okay, I'll be more mindful if that's the case. Okay, for all I, x is in Wi. Since Wi is a subspace, C times x is in Wi. So Cx is in the intersection of Wi as needed. Okay, and this finishes the proof. So let's conclude by the subspace test. Okay, arbitrary intersection. How do you spell intersection? My goodness, I just write this. Arbitrary intersection of subspaces is a subspace. Okay. All right. So that's an exercise, certainly worth doing, to practice the definition as well as some basic proof writing skills. Okay. And it doesn't have to be crazy difficult proofs. And just by doing these simple proofs, we can practice our proficiency. Okay. And mathematical writing. Anyway, so let's do the next section. Linear combinations and linear span. I posted a question, I think yesterday or something, on what's the span of the empty set. And I think the correct response rate was like 50%. So it's worth going back and check the definition. Okay. So in short, a span is the smallest subspace that contains a set. Okay, the span of A. A is an arbitrary subset. Okay, it doesn't have to be a subspace. A is a subset of a vector space. Then the span of A is the smallest subspace that contains it, that contains A. So if you have an empty set, A is an empty set, then the span of A has to be a vector space, it has to be a subspace. Right? It has to be the smallest subspace. A vector space must have 0. And the set 0 already contains the empty space. So the span of the empty set is the vector space 0. Okay, so it sounds a little bit funny because span in everyday English means to generate, right? To span is to generate. Apparently, in mathematics, something can be generated from nothing. The span of an empty set is the set 0, which is not an empty set. Okay. All right. The zero vector space. Yeah, you're correct. Yeah, the zero vector space. Anyway, so here, linear combinations. Because the commutative and associative laws for vector addition, the sum of, let me make that bigger. Can we enlarge that? Can we control plus? How does that work? How do I make the text a bit bigger? Because because the commutative and associative laws for vector addition, the sum of finite set of vectors is the same for all possible ways of adding them. Yeah, that's correct. Only because of these two laws. Okay, only because of, let's think about why. Here, for example, the sum of the 3 vectors alpha A, alpha B, alpha C can be calculated in 12 ways. Why 12 ways? Well, why 12 ways? I'm pretty sure this is a problem in combinatorics, right? Why 12 ways? So if you put them in different orders, all of which give the same result, right? So if you put them, so this is alpha A, alpha B, alpha C, and then you exchange the order. Ah, I see why. So if you have three vectors, right? Three vectors, A, B, C. I just call them A, B, C. Okay, A, B, C. You have three vectors. You can arrange them in 3 factorial ways, which is 6, right? And in each configuration, let's say A, B, C, you can, I'm saying from left to right, you have A, B, C, A, B, C. But where do you put the bracket? Right? There are 2 ways to put the bracket. So it's 6 times 2, which is 12. This is a problem in combinatorics. And they all give the same answer. Right? Therefore, if I, ABC, is the set of indices used, the notation sum of alpha I is in big I, indicates the sum without telling us how we got it, is unambiguous. Huh. You see, this is very nice. This is very rigorous. Okay, I like this a lot. Because we often write this summation notation without thinking that much, and actually it relies on the laws. Okay, if you don't have these laws for the addition, then this is a nonsensical formula. Because if the result depends on the order of operation, then it's meaningless. It's not well defined. Which indicates the sum without telling us how we got it is unambiguous. In general, for any finite index set of vectors, there is a uniquely determined sum, which we can compute by ordering and grouping alpha in any way. Yeah. And by the way, the index set I is often a block of integers 1 to n. Right? So it's like the sum I from 1 to n. You see this in stats a lot. Right? And here we denote m bar as the index set. Okay, sure. In this case, the vectors alpha I form an n-tuple, alpha I from 1 to n. Unless directed to do otherwise, we would add them in their natural order, okay, alpha 1 plus alpha 2 and so on, and write the sum as this one. So this is very common notation. I'll not explain that. Note that the way they are grouped is still, note that the way they are grouped are still left arbitrary. Okay, sure. Frequently, however, we have to use index sets that are not ordered. Index sets that are not ordered. Sure. For example, the general polynomial of degree at most 5 in 2 variables, s and t, is as such, where the finite set of monomials has no natural orders. Okay, so let's maybe draw a plane to visualize that. So you have I and j. I plus j, of course, I and j's are integers. Okay, and so we have this triangle-shaped set of points like this. 5, 0. Okay, so that's like that. So we're summing over this set. Any pair ij can come from these points. You can have 0, 5, 1, 4, and so on. Right. Remember, this is polynomial of degree at most 5. It can be less than 5. If it's strictly 5, then only these points are considered. Okay, so of course you can order them. It has no natural order. That's what it's about. Can we get some double counting to ensure that? Just kidding, haven't double counting the combinatorics in a while. I don't think we double count when we justify the number 12. Okay. Anyway, the formal proof that the sum of a finite collection of vectors is independent of how we add them is by induction. We leave it only for the interested reader. Do you give a flip? Apologize for my language. Do you give a flip? A finite collection of vectors is independent of how we add them by induction. Well, perhaps we would like to, I don't feel like doing that proof for now, okay, which is okay. I mean, don't feel bad about it. But I mean, I'm saying okay, I'm doing this, and that's okay. I'm being a self-rationalizing asshole. Okay, and I do think this is a good exercise for induction. Okay, I just want to get into the vector space stuff more. Okay, that's kind of I'm being greedy. Anyway, but even though I'm skipping the proof, I will formulate the statement. Okay, so let's think about if we want to prove this, what would be our target? What would be our goal? I mean, we need some sort of notations, right, to do proofs in most scenarios. So the statement is the sum of a finite collection of vectors is independent of how we add them. So let's formulate the statement. So here we have this is our goal, our target statement. Just write target statement. Okay, the target statement says the sum of a finite collection of vectors. Handwriting is truly horrible. I'll try to print instead of writing cursive. Is independent. And it's actually not that much slower of how we add them is how we add them. Okay, this is a statement. So this is the same as saying for every n in the set of natural numbers. Okay, we want to define something called a permutation. Let sigma n from the set m bar, right? M bar is the notation we use in the textbook. M bar, which is the same as the set 1, 2, all the way to n. To the same set. Let this be a permutation. Just to make sure everybody understand what a permutation is, for example, you have 1, 2, 3. That's the set 3 bar, right? And let's write the set one more time. Make a copy of that, and just define a bijection over that set. So let's say 1 is mapped to 3, and 2 is mapped to 1, 3 is mapped to 2. That's a bijection, and that's a permutation. This is a permutation. So we have this is a permutation. Give permutation. The sum over I in sigma, sigma n m bar. Hang on, is that the way we write it? Perhaps, yeah, I mean this. So, okay, let v1 all the way to vn, okay, be vectors in big V. Be vectors. Then v1 plus all the way to vn is equal to v sigma n of 1 plus dot 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 all the way to v sigma n of n. So this way, for an arbitrary or let's put it this way, for for every n in big N, for every sigma n, for every permutation sigma n, and for every n tuple of vectors, right? So that's why can't I use it? And for every n tuple of vectors. Yeah, that's the statement we wish to prove. That's our goal. And the book mentions we need to prove that by induction, which I will not do right now. Okay, I don't think I'll be doing that in any time soon. But yeah, in principle, that's the formulation, because sometimes the very first step in doing a proof is to formulate the statement in a way that is susceptible to apply a certain technique, right? For example, this sentence by itself is not a great starting point for proving it by induction. And now we have this n. You can consider, let's say, the base case proved by induction. Actually, proved by induction, I'm just going to walk through the structure, okay? Proof by induction, we prove the statement don't just say by induction, but instead we say by an induction on n. And this is standard phrasing. Induction on n. Okay? And then we start with the base case, n equals 1. And then we have the inductive case. Inductive case is typically the heart and soul of any induction proof. Right? So I'll elaborate on that. Basically the idea is assume the statement is true for all, assume it's true for n equals k. The statement is true for n equals k. So assume for some k, in big N. Actually, there's a choice that we have to make ourselves when we do induction. Do you use regular induction or strong induction? The regular induction only assumes the statement as true for n equals to a particular integer k, whereas strong induction assumes the statement being true for all integers less than or equal to k. That's the strong induction. And which method, well, which induction you should use, there's not a really many general guideline for that. It really depends on how well things go. What I do is I always start with a strong induction. If it ends up, okay, if it ends up that only n equals k being true is needed, then I'll modify the assumption to make that as a regular induction. Okay, it just feels to me that's more natural. Okay, you start from assuming the assumption for strong induction, and you do the proof based on that induction, based on that assumption. And if as it turns out, only n equals k is needed, then you modify the assumption to be just true for n equals k. So it becomes a regular induction, if that makes sense. This way, it saves you potential time. It potentially can save you time, because if you start from regular induction, right, and that's the original thought process for constructing the proof, and then it turns out that, oh, you need n less than k as well, and that will be starting over, right? So that's why I use the strategy I just mentioned. So for some k, let's use the strong induction hypothesis. For some k, for some k, for some k, for every j from 1 to k, and for every loads of quantifiers, for every sigma k from k bar to k bar, and for every k tuple. Is that k? No, it's j. My goodness. That's yeah, I made a mistake here. Okay, I'm doing the strong induction assumption, sigma j. Okay, I'm not promising that you would end up needing the hypothesis for strong induction, but if you can do the assumption for the strong induction, you already know how to do it for regular induction. For every j, okay, for every sigma j, no, for every sigma j, and for every j tuple of vectors v1 all the way to vk in big V, we have v1 plus all the way to vk equals to sigma k of 1 plus all the way to v sigma k of k. That's the inductive hypothesis, which we call IH. Okay, inductive hypothesis. And then we have the inductive step, IS. So you need to show this is true for k plus 1, for n equals k plus 1. So you are going to let sigma k plus 1 from the set k plus 1 to k plus 1 bar be a permutation. Right, let v1 all the way to vk plus 1 be vectors in k, vectors in v. We need to show v1 plus all the way to vk plus 1 equals v sigma k plus 1 of 1 plus all the way to v sigma k plus 1 k plus 1. And this is actual work. So you see, proof writing has a lot of mechanical parts as well. You can set up things, right, without actually knowing how to do this. These are mechanical steps. And don't ever estimate those steps, because often a lot of difficulty from proof writing stems from don't know what exactly needs to be proved. And whenever you are writing down, okay, something needs to be shown, that's, I would say, typically around 20% of the effort. Okay, and imagine this is done, you would close this inductive step as needed. Okay, and then finally, and you write therefore by PM, assuming that you do end up needing the strong induction hypothesis, okay, you would write by the principle of strong mathematical induction, the original statement holds, which is rather long. I will not repeat that again. Okay, the original statement holds. So that would be the structure of the proof. And I'm just leaving out the details. Okay. Using induction. A quick comment about induction versus strong induction. They're equivalent. Okay. It's really an unfortunate terminology because typically when we say in mathematics something is stronger, means something that is more fundamental, right? It's like in statistics, you have the probability theory, you have the strong law of large number and the weak law of large number. The weak law is implied by the strong law, but not the other way around. But here, strong induction and regular induction, in fact, are equivalent. They're logically equivalent. You can prove one from another. Okay, and they're in fact equivalent to the axioms of the for integers, for natural numbers. So it's really unfortunate terminology that we use the term strong. And I don't know why, who come up with this term. It's really miserable because in the strong induction, you assume more, right? And the general idea is if it looks like that you're assuming more, it makes the conclusion weaker. I don't know why this is called a strong induction. But mathematically speaking, strong induction and regular induction has no difference. I mean, logically speaking, it's just one turns out to be more convenient in certain problems than another. Okay, but they're logically equivalent. Anyway, we spend enough time on this part, okay, and I do hope the interested reader, interested viewers, would finish up what I just set up, because this is the detail. All right, the details that left to be left as an exercise to the reader, as the cliche goes. In order to avoid looking silly, okay, in order to avoid looking silly. And by the way, if you write this nowadays, if you type this in a, I don't know, like a Google Doc, and you have Grammarly installed, it would suggest this is two verbals, okay, and instead just write to avoid looking silly. The AI would recommend you to get rid of the in order. We begin the induction with two. Oh, actually, it tells you how to do the induction. Oh, it begins with two vectors. Ah, that's right. That's right. It should begin with two. N equals 1 is, there's no addition going on. So this is completely stupid. Okay, n equals 1 makes no sense. You should start from n equals 2 as a base case. Okay, did I do that correctly? I mean, I was using the permutation to codify the idea that you can use any order you like, right? Is independent of how we add them. Right? So that's okay. And let's see what's the author's phrasing. Okay, so n equals 2 is trivial. Suppose that the assertion is true for index at having fewer than n elements. You see, this is strong induction. It's assuming that the assertion is true for fewer than n. So it's one assuming it's true for elements for index sets with cardinality 1, 2, all the way to m minus 1. So actually, it does use the strong induction, it turns out. So that's I mean, I didn't know beforehand. I didn't read this before the stream. Indeed, I disagree with the Grammarly AI. In order here is fine as it is. Yeah, it's just a funny observation. Consider a collection, alpha I, of n members. Okay, so this is your set of vectors. Let beta and gamma be the sum of these vectors computed in two ways. Okay. So beta and gamma are the results of the summation, but in different ways. In the computation of beta, there was a last addition performed so that beta is the sum of alpha I where I is in J1 plus the sum of alpha I where I is in J2, where J1 and J2 partitions I, and where we can write these two partial sums without showing how they are formed. Okay, because here J1 and J2 have fewer elements than n, right? So the induction hypothesis holds for J1 and J2. I think this is actually a shorter proof than the one I just did. Then why this is given for the interested reader? When I read this, I assume, okay, they'll also just say, okay, we're moving on, and this is left for you, and it does the proof for us, perhaps with um, um, this is I guess this is more of a sketch of the proof, right? Because formally prove it, you would need to write it in this way: base case, inductive case, and blah blah blah. And this is a more discursive style. It's like the way I write explanations for my quizzes. I don't usually have the space to do a full proof, so instead I just give a sketch of the proof. Right. So that's the induction proof for this one. Very nice. Similarly, gamma is this one, and now we're okay. And now we set the intersection between. So here we have four such intersections, right? So I have J1 and J2, J1, J2, K1, K2. The intersection gives you L11, L12, L21, L22. So you have four sums. When it is understood that xi is the sum over alpha I, where I is in these intersections. Okay, makes sense. When we call the sum over an empty index set 0. See exercise 1.37. What's that for? Is that something that needs to be proved? 1.37. Actually, you know what? Let's go to the exercise right away in case we forgot. Is that something special? By convention, the sum of an empty set of vectors is taken to be a zero vector. This is necessary if the theorem 1.1 is to be strictly correct. This is necessary. Okay. Interesting. What's theorem 1.1? What is theorem 1.1? I don't think we have encountered a single theorem so far tonight. So, yeah, that's the theorem. Okay, we'll come to this later. So, this isn't just like a silly assumption. I mean, it sounds rather harmless, and it is harmless. But it turns out that there are certain results that would depend on it. That's the question is reminding us. Or the question is reminding us. Then you have the sum of J1. Why is that? Sum of J1. So we want to sum over J1, right? So L11 is the intersection of J1 and is that correct? I think it's correct. Because J1 is J1 union with OI. And I can be partitioned into K1 union. No. I mean intersect. J1, if J1 union I, we get the whole I. That's not what we want. So J1 intersect K1 union K2, and then you just distribute. Right, so this is correct. So you just get J1 intersect with K1 union J1 union with J1 intersect with K2 quantity, and that's what? And that's L11 union L21. So therefore, the sum over J1 is the result of summing over L11, which is xi11, and the result of summing over xi12. Xi12. Why not xi21, huh? Xi12? What's xi12? Xi12 is the sum over L12. Oh, right. I made the notational mistake. This should be the first index. You see, the first index is the index of j. So here I have j2 and k1 taking intersection. So this should be L12. This is L21. This is L21. This is L12, and this is L22. So yeah, that's correct. All right, which completes the proof. That's complete proof. Why are you saying it's only left for the interested readers? You're proving it. Pretty much, this is the proof. My goodness. Okay, this is the kindest professor ever, who said you're leaving it as an exercise and then end up doing the proof yourself. Okay, I love this guy. These two guys. A vector beta is called a linear combination of a subspace A. I don't think you will ever see a discussion. This is such a careful treatment on finite vector sum. I don't think you will see this anywhere. Not even in Sheldon Axler. No? Can somebody appreciate what I just said? Or not what I said. What I said does not matter. What the book just given. Has anybody seen in any textbook of such a careful treatment on the finite sum of vectors? I'm pretty sure every book, if ever, would say when it comes to finite sum of vectors, they either say, this always exists, and then move on. Here it actually gives an induction proof and tells you it does not depend on the way you sum it. Mind blown. Anyway, a vector beta is called a linear combination of a subset A. A subset is not a subspace. A does not have to be a subspace. Okay, and it does not have to be a finite set. It has to be a subset of a vector space. Okay, I think we can come up with some interesting example, and it's a good candidate for a quiz question based on that. A vector beta is called a linear combination of a subset A of the vector space V if beta is a finite sum of xi alpha I, where the vectors alpha I are all in A. It's a linear combination, and xi's are arbitrary. Xi's are arbitrary. So beta is a linear combination, huh? Thus, if A is a subset, what's that? T to the n, where n ranges from 0 to infinity, of all monomials, right? So this set, A here, is 1, t to the 1, t squared, t cubed, and so on. Right? All monomials. There's no highest order here. And by the way, what's this notation? R to the R. This is something we seen last time. So it means real valued functions defined on R. So remember we have the notation Rn. Last time we treated it as a function, a real value function defined on the finite set 1 to all the way to n. So that's the notation. Okay, and we can generalize that idea by simply replacing n by another arbitrary set A. So R to the A refers to the set of real valued functions defined on the set A. where A is a non-empty set. Okay, and that's the definition of R to the A, and it forms a vector space, a real vector space. Here, we have R to the R. So that's the set of real value functions defined on the real line. And of course, for each monomial, that's a function that's a function, right? That for each such monomial, that's a function in the set R to the R. And let's actually use the term vectors more. Each monomial is a vector in the set R to the R, because we're treating functions as abstract vectors. Right? So this set A of all monomials is, of course, a subset. Right? It's not a subspace. It's a subset. It's not a subspace. Because let's say t to the 1 plus t squared is not in this set. It's a polynomial instead of a monomial. Then a function f is a linear combination of a linear combination of the functions a if and only if f is a polynomial function. Yes, that's correct. Question, pop quiz. Is a power series, if f is a power series, let's say the sum never ends, is that does the power series count as a linear combination? Well, in general, it doesn't, right? Because here linear combination refers to finite sum, right? When we're doing infinite sum, that's a whole different beast. I suspect the reason that the author is being so careful with showing that finite sum is independent of the order you're performing, right? And that's based on the two axioms of vector additions, commutativity and associativity, is to hint that in general, addition or the sigma notation does not behave the way we just mentioned. Okay, in infinite sum is a meaningless symbol unless you assign a meaning to it. Okay, the meaning of this thing is not obvious at all. I mean, we know from calculus an infinite sum is taken as the limit of a partial sum, and that's a particular way to assign a meaning to this expression, sum of I from 0 to infinity ai. This in itself is meaningless. So if you write, let's say, a0 plus a1 plus a2, this in itself is just a meaningless expression. But if we understand this as a limit of a sort, then we can discuss it using, well, the theory of limits. You can discuss it using real analysis. The most common interpretation is a partial sum interpretation. Right? You take the finite sum, which is well defined by what we just showed here. Then you take the limit of the partial sum. And this operation we just defined, okay? This operation we just defined, the usual infinite sum in calculus, is not order independent. It's not actually order independent. If let's just take the ordinary infinite series in calculus, and if you change the order of operation, let's say you decide to group the nearby terms, seems like an innocent looking operation, right? It is not clear at all why this operation should agree with the partial sum definition. And here's a famous paradox used by a theologist with which I think it's called Grandi's series. Maybe you can find it in Wikipedia. This is something that actually happened. It's not just amusement. Okay, so Grandi's series. Grandi's series is here. One minus 1 plus 1 minus 1. This is called the Grandy series. So this priest, Grandy, argued that this proves that God exists because something can be created out of nothing. And that's because you can group this in different ways. And of course, mathematicians were horrified. Right? So because of these paradoxes, a rigorous definition, or the rigorous definition you find in real analysis, calculus, was formed in order to rule out these pathologies. Okay, and let's just think about why this is wrong. Okay, in the standard calculus definition, why this operation is wrong. So let's write it. Let's read the identity this way: 0 equals 1. Okay, 0 equals to 0 plus 0 plus 0 plus blah 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 is equal to 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. And then you group it in a different way, and you leave the first one intact, and equals 1. So let's read the identity, read the deduction from this order. According to the standard calculus interpretation of infinite series, which step falls apart? Well, 0 equals to the sum of a bunch of 0 is correct. This is an infinite series. Every partial sum is 0, so it converges to 0. So 0 equals to the sum of infinitely many 0 is fine. That's okay. That's okay, right? And here we're just rewriting each 0 as 1 minus 1, and that's also okay. Because each 0 is 1 minus 1. This is also okay. But this operation is not okay. Grouping is not okay. Regrouping is not okay. Okay. In analysis and calculus, and I strongly recommend you go to Baby Rudin, the series chapter, I think it's chapter 3, to see the most comprehensive treatment on series. Well, I'm probably not the most comprehensive, but fairly comprehensive treatment on series. There's a discussion on rearrangement. So what we can say about rearrangement of series? Well, it needs to be a convergent series. And here the series is divergent. Right? This is a divergent series. So divergent series does not allow for rearrangement. Okay? And it's not even sufficient. It's not even sufficient, okay, for a series to be convergent in order to rearrange it. Simply being a convergent series is no guarantee that you can do rearrangement. It has to be absolutely convergent. And that's the whole point of introducing absolute convergence. It's something that typical courses on calculus does not mention. Well, in typical calculus, you learn the notions of absolute versus conditional convergence, but not really why those notions are useful, unless for some specific convergence test. Okay, if you can show it's absolute convergence, then it's convergent. That's about it. But their real significance lies in the study of rearrangement. If the series is absolutely convergent, then you can rearrange it however you like. But if a series is only conditionally convergent, then something really nasty can happen. And something really nasty can happen. You can still discuss convergence. Okay, conditionally convergent series, you can still assign limits to it if you take the partial sum interpretation. But if you change the order, there's actually a whole range of values that the conditionally convergent series can take. This is called the Riemann series theorem. I think it's called the Riemann series theorem. Let me just quickly Google that. Riemann series theorem. And this is not something usually covered in typical calculus text. For example, this is a famous, where is that? Yeah, this one. Alternating series. Yeah, this is the alternating series, right? Hang on, which one? Yeah, this is a famous alternating series that converges to the natural log of 2. But you can regroup them and have it converge to different things. And this is a classic example. So go to this article, Riemann series theorem, to really appreciate that infinite series can have a really weird rearrangement behavior, right? So yeah, which makes the proof here looks less silly, right? This is not just being pedantic. Nightmares exist for infinite sum. So better make sure finite sums are well behaved. Okay. Anyway, here let's go on. If A is finite, it's often useful to take the index set alpha I to be the whole of A. Make sense? And use the zero coefficient for any vector missing from the sum. Right? And that's actually, I guess, the most common form of linear combinations you would encounter in linear algebra course. You say the linear combinations of a finitely many vectors. Right? If some vectors is missing, you simply put a zero coefficient in front of it. Right? So if A is a subset, sine of t, cosine of t, e to the t of r to the r, okay, then we consider A as an ordered triple. Makes sense? In the list ordering, and the function 3 sine t minus t minus e to the 3 sine of t minus e to the t can be written as 3 times sine of t. Cosine is missing, so we put a zero coefficient in front of cosine. And minus e of e to the t is just minus 1 times e to the t. That's a linear combination of the triple A with the coefficient triple 3, 0, minus 1. So this is the coordinate. So this function, 3 times sine of t minus e to the t, relative to the basis, sine of t, cosine of t, e to the t, has a coefficient triple or the coordinate vector of 3, 0, minus 1. Okay, so that's linear combination. Let's make a quick quiz question real quick. Question. So let's consider a let's consider the quarter of a circle. Quarter of a disk. X squared plus y squared less than 1, and x and y both positive. So it's just the unit circle, the part of the unit circle in the first quadrant. This is A. Let's call that A. What's the linear combination of A? What's the set of all possible linear combinations of A? What is the set? What is the set V in R2 such that V is a linear combination of vectors in A? What's that? What's that set? Can we answer that question? Sure, we can. Well, if you have two vectors in there, if you have finitely many vectors in A, you take their sum. I think it can be the whole of R2, right? Because let's just take a simple example. So let's say you pick any. Hang on. Can we? You can pick any fixed direction, so to say. Let's pick any vector whose endpoint is in the disk, like so. And then you can just scale this one. And then you can just pick one vector Pick one vector in A. And here, because A is an open set, okay, it does not include the boundaries. So general vector in A looks like this. And you can scale it. Now use to both directions, right? Extend it to both directions. And you can do this for arbitrary direction. So this way it is clear that all the vectors, except those that are on the x-axis or the y-axis, are in the linear combinations of A, right? Because in a linear combination, the coefficients can be arbitrary scalar. So so far everything except the coordinate axis can be attained. It can be attained by linear combination. You simply pick an arbitrary non-zero vector in A. I mean, A does not contain zero vector. So just pick an arbitrary vector in A and you scale it in both directions. You end up covering the entire plane except for the two axes. But can you cover the two axes? Can you do that? Can you cover the two axes? That's the question. No, I don't think you can, right? Can you cover the axes? Can somebody ask and say something to comment about that? I don't think you can, because can you do that? I'm really struggling here. Is it possible to get let x and y, so to say, in A? Is it possible for C1 for let's say alpha x plus beta y to be the vector 1, 0? Can we do that? Do such x and y exist in A? So I want to have a direction on the positive x direction. I want to have a vector on the positive x direction by taking linear combinations of the vectors in the quarter disk. Can we do that? Well, let's try. Let's say x is x1, y1. This is x1, x1, x2. Y is y1, y2. So we have alpha x1 plus beta y1 is 1. Alpha x2 plus beta y2 is 0. And because the two vectors are in the quarter disk, so they're all positive. The coordinates are all positive here. They're in the first quadrant. So alpha and beta has to be in opposite sign in order for the second equation to hold. Right? X2 and y2 are both positive. So alpha and beta must have opposite signs. Can the first equation hold? I think it can. Nothing that screams it cannot, right? You know, I'm gonna do something and use generative AI. You know, I'm not pretending I never use AI. Let's try use AI. So here, just click Ask Gemini right here, and say, and yeah, I disagree. Okay. Anyway, this is consider the quarter disk. Let's call it A x y such that x squared plus y squared. It might be something that's really silly that somehow missed. I think it should be possible. Y greater than 0, the quarter disk. Can the linear combination of two vectors, it doesn't have to be two, right? Linear combination only needs finitely many vectors. Can the linear combination of two vectors in A be 1, 0 transpose? It cannot. It cannot. Right? I mean, I was drawing the picture. I was thinking, it does not feel that way, huh? It turns out it cannot, huh? That's what the AI said. Let's try to read critically, okay? A linear combination of two vectors in A cannot equal 1, 0. And here's the direct mathematical reason why. Yeah, this is what I wrote. Let's look at the second equation. Since, we thought about that. The sign and C1 and C2 must be opposite. Without loss of generality, assume C1 positive, C2 negative. Yeah, nice. We can write C2 as minus C2 absolute value. Yeah, that's true. Substitute it into the first equation. Because both vectors lie in the unit disk, the x-coordinate are bounded by 1. Ah, right. This is very subtle, which I did not thought about. You see, here x1 is less than 1. x1 is less than 1, so x1 times c1 must be less than c1. Must be less than c1. But on the other hand, for the equation to be equal to 1, 1 must be less than c1. So there's the contradiction, no? So c1 is greater than 1. No. There's no contradiction yet. Okay, no contradiction yet. So 1 is less than c1. Okay, if c1 is greater than 1, let's revisit the y-axis equation. Since c1 is greater than 1, the absolute value of c2 must also be larger to balance it, right? Because you have what? The y-axis relation. Yeah, the y-axis relation. Since c1 is greater than 1, c2 absolute value must have to be relatively low. Why? We didn't assume any relations between y1 and y2. Wait, hold on a second. Geometrically, any linear combination where the coefficient is the opposite sign represent the line stretching in the fourth quadrant. Yeah. To cancel out the y components perfectly into x-axis exactly, x equals 1. The positive vector would have to extend the pass boundary of the unit disk. Because the original vector is strictly trapped inside the open boundary, they lack the reach to scale down to 0 simultaneously while reaching. I don't fully get this. Actually, I don't fully get this. But let's just keep asking. Can any linear combination, right? I used two vectors in the first question. Can any linear combination of vectors in A be 1, 0, right? And linear combination, we always use finite sum. Let's tell AI that. And we only use finite sum for linear combinations. Yeah, that's the question. So what does Gemini think? No, it's absolutely impossible for any finite linear combination of vectors in A to equal to 1, 0. While the previous geometric intuition showed why this fails for two vectors, the algebraic restriction hold true no matter how many vectors n you choose. to use from the quarter disk. So let's consider a finite set of vectors belong to the open quarter disk. So let's add them and impose that to be 1, 0. You have two equations, yes, right? The x coordinate equation and y coordinate equation. So there's a contradiction apparently. Huh. I mean, uh, I didn't saw too hard when I was making this question, but apparently, okay, assuming whatever AI said is true, okay, I have to look deeper, and I wanted to make that a quiz question. It turns out that the two axes cannot be attained, right? I mean, assuming what AI says is true, that means the axes cannot be attained. So the set of all linear combinations of vectors in A consists of the four open quadrants and the origin. Any origin, because you can always take the scalar to be 0 and you get the origin. But never the axes. That is something I never encountered before, huh? I mean, I'm a little bit, I feel a little bit uncanny because, and here's the gist, because when I took linear algebra, I remember seeing a definition of a span. The span is the set of all possible linear combinations in the set. I'm pretty sure some of you guys heard of that too, right? And there's a theorem that says span is always a subspace. A span is always a subspace. But here we just seen that if the axes cannot be attained by linear combination, that's not a vector space. So this, I mean, let's just keep pushing the AI. So by this logic, the linear combination, I mean, I have to clear this proof. I mean, I have to parse this myself. But it's just, by this logic, the linear combinations, the set of all linear combinations of vectors in A, the quarter disk, cannot cannot be in the direction of x and y axes. That's exactly right. You have caught on to the core geometric restriction here. I mean, AI tends to be very agreeable. You know, this is something we have to be very careful about. So according to this logic, in fact, it can't even be the origin. Y cannot be the origin. I think it can be the origin, no? It can be the origin. This is rather sketchy. It can't be the origin. I mean, this is rather embarrassing. I mean, I made a question I cannot answer myself. And I think it's a good idea for me to redo everything from scratch and think about this carefully. It can't be the origin. You just take any non-zero, take any vector in A and multiply by 0. That's a linear combination. No? You gotta By the strict textbook definition, however, in the context of pure non-trivial balances. But anyway, like, this is totally bizarre. So the reason I am doing this example is that I've seen different definition for the span of a subset of vector spaces. Okay, let A be a subset of a vector space V. Some books say that the span of A is the smallest subspace. So by this definition, span of A must be a subspace, is the smallest subspace of V that contains A. So according to this definition, the span is always a subspace. But some books say that the span of A is the set of all linear combinations of vectors in A, which can be shown that it is span is always a subspace, is always a vector space. So the two definitions agree. But here, in the quarter disk example, the set of linear 9, what's that? A set of linear combinations of vectors in A, 9. What's 9? How is that relevant here? The set of linear combinations of vectors in A is not a vector space. As it does not include the coordinate axes except 0, except the origin. So this is bothering me. What? Stop with this kind of nonsense, man. Just tell me what's going on. I'm being annoyed. Like, this is AI doing some rather disappointing saying, what is your experience of clash between the definition of set of vectors versus definition of a subspace? Feels like a slight misinterpretation of what happens with quarter disk A when we take this linear combination. The set of all linear combinations of A is actually a full vector space, specifically, yes, the entire. That should be the case, right? So why couldn't we take the axes? What happened here? Resolving the paradox. The previous proof showed that you cannot get 1, 0 directly if your positive coefficients are strictly bounded by the boundary condition. No, I'm not. I'm using any real combinations. I'm using any real combination. So how do you? Oh, okay. I'm being super silly here. I'm being super silly here. So let's say you're we're allowed to scale the vectors in A using whatever coefficient we want. So let's construct a parallelogram. So perhaps this way. Can we do that? This is 1, 0. Okay, this is 1, 0, and let's do perhaps this is 1/2. Let's do 1/2, and this is 2, 1/2. 2.5. And how do we construct a parallelogram? Oh, easy. Just be like this. So you have -1 and -1/2. Okay, I was being rather silly. And we can scale these two vectors accordingly so that they stay in A. So 1, 0 is entirely achievable. So 1, 0 is entirely achievable. Okay, I was struggling over nothing. And this happens. I mean, yeah, it's embarrassing. So you can just multiply that, multiply 1 minus 1/2 by an appropriate scalar so it stays in the quarter disk. Let's call that vector v1. And we scale the 2 1/2 appropriately so it stays in the quarter disk. So you can see v1 and v2, they lie in A. So we want c1 v1 plus c2 v2 is 1, 0. And this is entirely achievable. Right? c1 v1 is 2 minus 1/2. c2 v1 is -1. Oh, sorry, the 2 and 1/2 minus 1 and minus 1/2. Okay, and then you choose c1 and c2 appropriately so that v1 and v2 are in a quarter disk, which we just seen is entirely possible. Right? So, therefore, the set of all linear combinations, okay, when we're taking linear combinations, the coefficients can be arbitrary, and this way, there's no so-called reach problem. Okay, so this is useless discussion. Let's close that and pretend that never happened. Okay, so yeah, this set is simply R2. Because after you get 1, 0, you can scale it wherever you want. And similar reasoning gives you all the vectors on the y-axis too. Okay, so yeah, the quarter disk spans the whole R2. And the two definitions are equivalent. So we have two definitions for the span. One is the smallest subspace that contains a set. Right. Another one is more computational. Right. Another one is it gives you a recipe of how to generate elements in A. Right. Just pick any arbitrary finitely many vectors in A, take the linear combination, and whatever you get is in the span of A. Right. One of these two definitions gives you a recipe to construct the span of A. So here there's no weirdness going on. Okay, so this question will not be on a quiz. Perhaps we will. Like, I mean, I'll let you guys decide. Do you guys want to see this question on the quiz? Consider a quarter disk. What's the set of all linear combinations of vectors in a disk? Do you think that would be a good question for tomorrow? Anyway, let's get back to the main text. Okay, here, now consider the set L of all linear combinations of the two vectors, 1, 1, 1, and let's draw the pictures. What's 1, 1, 1 and 1, 0, 1, minus 1? It's the set of vectors, blah, blah. It should be a plane, right? It's 2, 3 vectors. Taking arbitrary linear combination, you should get a plane. It will be clear on inspection that L is closed under addition and scalar multiplication. This is true. It's a subspace, and therefore it's a subspace of R3. And also L contains each of the two given vectors with coefficients pair. And also L contains each of the with coefficient pairs. Yeah, that's right. Because you can treat these two vectors as a basis for L. So trivially, the first vector relative to this basis has coordinate of 1 and 0. And the second vector relative to this basis has coordinates 0 and 1. That's certainly true. Finally, any subspace M of R3 which contains each of the two given vectors will also contain all of their linear combinations. Yeah, that's true. That is L is the smallest subspace. Right? L is the smallest subspace. And by the way, how do we formalize this smallest subspace idea? How do we formalize that? Well, what do we mean by smallest subspace? You can use the idea of arbitrary intersection. L, as the smallest subspace of R3, as a formula, is simply the intersection of all Wi's. And remember, the index set can be arbitrary. It does not have to be a set of numbers, 1 to n. Right? You can use the index set as such. The index set is Wi is a subspace. Let's put a subset and the SP under to indicate the subspace. Wi is a subspace of R3. Here you use R3, and Wi contains what's that? The two vectors v1 and v2. Okay, so this is our index set. The index set consists of Wi's. Okay, the index set consists of Wi such that it contains the two vectors. Let's call them v1 and v2. And Wi itself is a subspace of R3. So this is our index set. And we just proved in the first exercise we did in the stream that the intersection of subspace is a subspace. And of course, by taking intersection, you are shrinking down the set. Right? If you take A intersect with B, two sets taking intersection, the intersection of A and B is less than A and less than B. And here we have this closure property of subspaces under arbitrary intersection. So L has to be the smallest subspace that contains the two vectors. Okay. It is called the linear span of the two vectors, or the subspace generated by the two vectors. Okay. So this is, if I do digress, there's something very similar happening in not in linear algebra, but in measure theory. So in measure theory, you also have this notion called a sigma algebra, and the sigma algebra generated by a random variable. And it's essentially the same idea. It's the same, structure of reasoning. Okay. So I'm just mentioning this in passing because I don't want to digress into measure theory because too much. Okay, I already digressed into measure theory, but just want to complete that. So first, in measure theory, we have this class of family of sets called the sigma algebra. So over sigma algebras, you can define measures. Okay, for each set in a sigma algebra, you can assign a notion of measure or like a size to it. Okay, and it is a property of sigma algebra that arbitrary intersection of sigma algebras is another sigma algebra. Okay, so that's the idea. So we have say a subset. Let's say we have a subset of the sample space. Have a sample space, okay, and we have a subset of that. We want to find the smallest sigma algebra that contains that set, that event. Okay, so what do? You take all the sigma algebras. You take all the sigma algebras, the collection of all the sigma algebras that contains A, and then pick their intersection. And that gives you the smallest sigma algebra. And this collection is never empty. This collection is never empty because the power set always contains every subset. Right? So this whole process is rather non-constructive. Right? Here, if you have two vectors, you can take the linear combination. You can take the linear combination and produce. I mean, love the content. Thank you so much. Did you just join the stream? Welcome to the stream. Or did you have been staying for a while? Hi, Mason. Yeah, so I was saying that what I'm trying to get to is that there are two ways to define subspaces. One is constructive and one isn't. Constructive in the sense that you have a way to generate elements in the subspace, if that makes sense. A non-constructive, hi, and a non-constructive definition is one you can argue that it exists, but you don't know what it elements look like, right? So here, let's say you have a collection of subset. Sorry, you have a collection. So first of all, you have a collection of vectors, or a subset, basically. So you have a subset of a vector space. We're going to define the span of that set this in a non-constructive manner. How do we do that? Well, the span is the smallest subspace of the vector space of the universal set that contains the set A. That's a non-constructive definition. It is a valid definition. It is a valid definition because we can show that such a smallest subspace exists. We can do that. Why? Because first of all, we have, you know what? I should really write it down, right? I've been talking over thin air without writing anything down. My apologies. Two definition of spans. Okay. Two definition of spans. Let V be a vector space. Let A be a subset of V. Okay. Definition one. And this is non-constructive. This is what I was trying to get to. Okay. This is non-constructive. The span of A is the smallest. Should I put a bracket to make things clear? The span of A is the smallest subspace of V such that that contains A. That contains A. So that's the non-constructive definition. So by writing this definition down, it immediately prompts the question. That, okay, why does such a smaller subspace exist? Right? So in order for this definition to be valid, we need to show that there exists such a smaller subspace. And here is how we go about proving it. Proof. Definition one is valid. Prove that the definition one is valid. And it goes like this. Let W be a subspace of V such that W contains A. Such W exists since V contains A. You can just take W to be V. Right? Because V itself is a subspace of V and V contains A. Such W exists. So let's now define the the script is C. Okay, script is C to be the collection of subspaces W subspace W contains A. Okay, I want W to contain A, such that W is a subspace of V. And we just show that C is not empty. It's not an empty collection. C is not empty as C contains V. As C contains V, right? So that's the property of C. And now we take L to be the intersection of all the W's where W belongs to scripted C. So we're just taking the intersection of all the elements in C. Remember, C is a collection of subspaces that contains A. Right. So by one of the exercises we did earlier, by actually this very exercise we did earlier, intersection of any family of subspaces is still a subspace. Right. So take L as the intersection of all the W's in C. Then, by an exercise, L is a subspace of V. L is indeed a subspace of V. L is a subspace of V, and any other subspace in C contains L, by the virtue that L is the intersection of them all. And for any W in scripted C, so we're talking about any subspace that contains A, W contains L. So L is the smallest, therefore L is the smallest subspace. That contains A. So L exists, right? The smallest subspace exists. Therefore, the first definition, even though it is non-constructive, it is well defined. So by writing down this definition, we have absolutely no clue what the span looks like, what its elements look like. But we do know that it exists. So this finished the proof of existence. And what I was going off a tangent, is that this is very similar in measure theory of how we prove that the smallest sigma algebra that contains a set or several sets exists. Okay, it's all non-constructive. We have no clue what the span look like according to this definition. But then you have the alternative definition, which is constructive. The constructive. So by constructive definition, the span of A is defined, is the set. The constructive definition is the set of all linear combinations of vectors in A. So that's the second definition. So here, this is constructive because we know how to calculate linear combinations. It generates, right? It gives us a recipe. It gives us a recipe to generate elements in A. So that's constructive. And of course, it remains to be proved that these two are equivalent. The constructive and non-constructive definition are the same. Right? So, I mean, you can start from the constructive definition and prove that any it is the smallest. You can start from the constructed definition of the span. You take the span as defined in the second definition, and you prove that this set is indeed the smallest subspace that contains A. So here's the proposition. Definition 1 is equivalent to definition 2. There's a proposition. So to prove that, you really need to prove two sets are the same. Right? You need to prove that two sets are the same. So the first set is defined as such. W, you need to show. Once again, go back to basic proof writing skills. Need to show. Let's first formulate our target. Target statement goes like this. W, you need to show the intersection of W. W belongs to the script is C. Script is C is defined this way. Need to show this is equal to the set of X such that X is a linear combination of vectors in A. Okay, I should have written this down a lot earlier because I was talking to thin air, and I'm pretty sure a lot of people got confused and left the stream. My apologies. I'll improve it next time. Okay, so this is what we need to show. We need to show these two sets are the same. And how do we prove two sets are the same? Well, we use a double containment strategy. Right? Use a double containment strategy. So to show that the second containment, you show that the right hand side is a subset of the left hand side. You let X be a linear combination. I'll stream to another 20 minutes and I'll stop because it's about 10 in the evening and I haven't even had dinner, which is why I made a few silly mistakes. Probably why I should have eaten dinner because I just got back from church in the afternoon and the traffic was bad. So I had to do the stream without having dinner. But anyway, I digress. Let X be a linear combination of vectors in A. So that's the that's where we start from, and we need to show X is in the left hand side. Well, what's the left hand side? Left hand side is the intersection of all W's, and what's that? Well, that we need to show that X is in every such W, is in W for every W in C. So that's the first direction. And the opposite direction is simply to reverse these two conditions. So we need to prove the other direction. You let X to be in W for every W in script C, and you need to show X is a linear combination of vectors in A. All right. So after this is done, then we can confidently say that the two definitions for the subspaces are equivalent. Okay, I'm leaving out the details here. Okay, so that's it. Okay, a question for the chat: have you guys seen, or have you guys seen these two definitions of the span? And have you seen a proof of equivalence of the two definitions? Actually, you know what? Let's go check out how does Axler treat the subject. Linear algebra done right. I have the PDF. And by the way, it's a free book. I mean, I've been Axler's I've been a big fan of Axler. The linear algebra done right. And people ask me what would be a reference on abstract linear algebra. I always say that book because it has a big readership, and I figured why not? It's a good book. So let's go to the definition of span, index span. How does Axler define span? 29. Yeah, it's the smallest subspace. smallest containing subspace, right? That's the span. No, that's the theorem. That's not a definition. Okay, here's the definition. But this is the definition for finitely many vectors. We're talking about general subset in our discussion there. And the span of an empty list is defined to be 0, okay? Here it's treated as a definition, right? In my quiz, I actually proved it. Because here Axler defined the span only for finite set, right? Whereas the smallest containing subspace, hang on, here, my point is that here we're dealing with only a span of finite vectors, finitely many vectors. But in Loomis and Sternberg, we're dealing with a span of any subset A of vector space, right? So I think Axler's treatment is less general. Does it have a span of arbitrary sets? It's just the span of a list, huh? Okay. Okay, I mean, so Axler does not give the proof that we just sketched. Okay, we just outlined. And there's no distinction between the constructive against non-constructive definition of the span. Okay, right, so yeah, because we don't have a lot of time right now, let's keep going. I'm just giving out the sketch of the proof. And this should work. This should work. I mean, unless you actually do it, unless you actually write the whole proof, you never know, right? I think they should be equivalent. Otherwise, there's going to be some major problems in elementary math, right? So these two definitions for span are both widely used. But as you can see from the surface, it's not clear they're equivalent. Right? So it's something that needs to be proved. All right, let's keep going. Is a linear span of two vectors the space generated by the two vectors? In general, we have the following theorem. If A is a non-empty subset of vector space V, then the set LA of all linear combinations of the vectors A is a subspace, and it is a small. That's what we wanted to prove. That's what we wanted to prove here. That's what we wanted to prove. Definition 1 equals definition 2. So here, let's read the proof and try to do the two-column method mentally. Okay. And this is very nice. The author does not skip steps and instead use the standard proof writing technique. You look, the way of proof writing is that it is always based on the logical structure of a statement. Most often, the statement we want to prove has the format of if-then, right? If-then, and for such statement you start by assuming the if part. So we need to assume that A is a non-empty subset of a vector space, right? And then prove the then part. Here, in the proof, it starts from suppose that A is finite. Okay, suppose that A is finite, and assume that there should be another situation if A is infinite. Okay, A is infinite. Okay, let's first look at the finite case. If A is finite, we can assume that we have index A in some way, sure, so that A is equal to A alpha, alpha I. I is in big I for some finite index set I, and every element LA, by the way, LA, this is the set of all linear combinations of vectors A. Okay, So LA has elements of the form sum of xi alpha I is in big I. Okay? And now we have, I is a finite set, by the way, because here A is finite. And then we have this sum, the sum of xi alpha I. The subscript or the range of the summation is suppressed. So I'm assuming this is sum over big I. The sum of xi alpha I plus the sum of yi alpha I equals the sum of xi plus yi times alpha I. Yeah, this is totally correct. This is totally. Let's think about what is it doing here. What are we doing here? Why do you write this seemingly obvious equation? We're trying to prove this is a subspace, aren't we? We're trying to prove this is closed under addition. So by this equality, we know that LA is closed under addition. And by this equality, LA is closed under scalar multiplication. And LA is obviously non-empty. LA is obviously non-empty because you can pick one of the xi's to be 1 and the other xi's to be 0. Then the sum would just be alpha I, and alpha I obviously belongs to A. And so LA is non-empty. Right. So here, and by induction, and by mathematics, why do you need induction? Well, I suppose here we're dealing with the finite set with number of elements n. Right. You can start with you can start with two vectors. Right. You can start with A cardinality equals 2. So you have two vectors. Suppose you have two vectors, and then that's your base case, and you assume that the statement is true when the cardinality of A is n, and you can use induction to prove that for any finite set, the LA is a span. LA is a subspace. You can do that. And moreover, LA contains each alpha I. Yeah, LA contains each alpha I because, as I said, you can just pick xi to be 1 and the other xi's to be 0. So it also includes A. Yes, that's correct. Finally, if a subspace W includes A, then what happens? Yeah, if a subspace W includes A, then W is closed under addition and scalar multiplication. Each alpha I is in A, so it must contain all the linear combinations. So it includes LA. So that's pretty much it. So this sentence proves that L is the smallest. Is the smallest, right? So every subspace W includes A also includes LA. So LA has to be the smallest. So this proves the statement for A being finite. Therefore, LA can be directly characterized as a uniquely determined smaller subspace which includes the set A. Okay, so that's good. And now we're doing the second case if A is infinite. If A is infinite, okay, we wish to prove the same thing. We still wish to prove that LA is a subspace, and we want to prove that LA is the smallest subspace, right? So basically, the other non-constructive definition we were talking about. So obviously, A cannot use a finite listing. However, the sum from 1 to n xi alpha xi alpha I plus the sum of yj beta j ranges from 1 to m of the two linear combinations of elements in A hang on. So here we're because here things are a little bit fast written. I guess I'm not okay. So based on the context, it should be clear that alpha I and beta j's for all I and j are elements of A. Okay, so for the first group, we're taking a linear combination of all the alpha i's. For the second group, we're taking all the linear combinations of beta j. This sum is clearly a finite sum of scalar times elements in A. Yes, that's correct, because alpha I and beta j's all belongs to A. If we wish, we can rewrite it as, okay, you can put it into a single sigma notation, right? And that's really not doing anything at all. You're just renaming the letters. You just renamed beta j's to be alpha m plus j and yj's to be x m plus j. So it becomes a single sum. In any case, LA is closed under addition, and multiplication by scalar is also a subspace. Why is the smallest subspace? Here we only prove that LA is a subspace. We didn't. Why is also the smallest subspace? It didn't say. Can we use the same argument? Can we use the same argument? Well, if W includes A, it also, yeah, it's the same argument. Therefore, this sentence is not written twice. It's the same argument that still works here. If W includes A, even if A is infinite, the linear combination only contains finite sum. So the argument still works. Okay, so yeah, that's the proof that shows the two definitions of the two definitions of span are equivalent. And this is done more generally compared to Axler. We just saw Axler. So that's why we don't just use one book. And this is another meta lesson here. Even though Axler's book is widely respected, I like it a lot. Right? The definition of span, although this is typically how you work with span in practice, you take the span of a finite list, right? But in general, the notion of a span really extends beyond that, right? And here, what's more elegant about the second definition, right? Because we can we've just seen the span can be defined as a smaller subspace. If you use that as a definition, you don't need to define the span of an empty list separately. You don't need that; it's already implied. That was the answer of yesterday's quiz. The span of an empty set is a zero vector space. And somebody commented mathematical shenanigans. The definitions and shenanigans, which I kind of agree. But the point is that the non-constructive definition is more succinct compared to the constructive definition. Here, in the constructive definition, the span of an empty set has to be separately defined because the formula no longer makes sense. But the smallest containing subspace definition still works. And you can derive the span of an empty set to be the zero vector space using that definition. Isn't that kind of nice? It's kind of the same application as RA. AC. What's advanced calculus like? Real analysis? Actually, there's a lot of overlap. Okay, advanced calculus. By the way, this one, this is not even advanced calculus. This is like 70% of, not 70%, but a huge chunk of undergraduate mathematics. It contains things like differential geometry as well. So, but in general, the term advanced calculus in North America refers to a proof-based calculus, a proof-based course in calculus. Yes, has a lot of overlap with real analysis. And actually, you know what? I'll give a book recommendation on advanced calculus in the North American sense of the word. It's Advanced Calculus by Folland. Anybody heard of Folland? Raise your hand in chat. Calculus by Folland. Gerald Folland. Yeah. So this guy, Folland, I can safely say are one of the uh, graduate students' most feared name because his real analysis book are very tough. So this is wow. You can even you have the full link here. Is that legal? Don't tell anybody I showed it on the stream. Okay. So basically, that's the typical advanced calculus standard, gold standard, basically. So that's mostly still. It's like a balance between calculation and proofwriting, if you know what I mean. So you will discuss something like completeness, compactness, uniform continuity in advanced calculus, but not so much in regular calculus. Okay. No means never heard of Folland. Um, like you check out his work. Check out his work. I strongly recommend his stuff. This is a good book. This is an excellent book. Even though it's kind of I don't know if it's legal to show this here. Is it legal to show it here? Because it's from the U of Washington website, and Folland works there. So maybe that's he decided to make the book public, like Loomis and Sternberg. But makes no mistake, the Loomis Sternberg book is insanely hard. This is by undergraduate standard. This book is insanely hard. It covers things like exterior calculus, um, differentiable manifold, Lie derivatives, Riemann metrics. that's um, that's differential geometry, man, and classical mechanics. And this is classical mechanics treated by differential geometry. So this is the name advanced calculus does not do justice to the content of this book. Well, but this is how Harvard Math 55, so different standard, I guess. What's your major? Applied math and stats. That's my major in the uni. Okay. Does that answer your question? So, yeah, there's that. I think it's over 10. Mine is operational research. Excellent. A lot of probability stuff and optimization, I suppose. Um, a lot of statistics, probability, and perhaps um, stochastic processes. When it comes to math stuff, like I guess perhaps queuing models and, and optimizations, linear programming, network optimization, that sort of stuff. It's very cool. Do you guys even have an operational research major in the States? Do you guys have that? Operational research is is that a you do machine learning still? Yeah, I did machine learning stuff. I did machine learning stuff. Yeah. Yes, I didn't like the stat classes. Oh, that's a shame. I mean, it seems to me, I'm right now. I'm just chatting with you guys. Okay, I'm kind of tired, and I don't want to just close the stream right away. Let's have some more casual chats. Yeah, I just feel like stats classes are kind of underrated in the math department because a lot of people think they're kind of boring and dry and nowhere as respectable. I mean, I'm using a very controversial choice of word, that's so to say, let's say compared to um, differential geometry. Stats is kind of considered as something messy and like it just. I mean, it has this impression, right? So typically, what happens in in North America, in the North America undergraduate program, is that all the math majors, I mean, math major as an umbrella term, okay, can be all sorts of math, applied, pure, even computer science is sometimes considered math. They're required to take intro stat. Are you doing your PhD? No, no. I only have a master's, as I said earlier in part of the stream. Maybe I'll do a PhD later in my life. But I've been um, consistently in the uni and after uni studying math on my own pace. So I'm not doing a PhD right now. So there's uh, what I was talking about. There's just two, perhaps maybe even one, two mandatory courses, one on probability, one on stats, like everybody in the math department needs to complete. And it feels rather crammy. Just think about it. So in the probability course, sometimes the probability and the stats is combined into one course, which makes things even more crammy, in my opinion. So you have to memorize a bunch of formulas, more than pretty much any other math subject at the same level, right? So let's say if you're in a second year doing your intro to stats course, what other math subjects you would likely encounter at that level? Maybe Calc 3, maybe linear algebra 2, maybe intro to differential equations, things like that. Maybe intro to numerical analysis, right? Because at that stage, um, people are usually not that advanced to take things like um, abstract algebra or real analysis yet, right? So the stat class kind of stands out as the crammiest of all. You have to memorize all sorts of like test statistics and just mechanical procedures to calculate stuff, and there's barely any intuitions being, let's say, simply the courses don't have the time, right? They want to kind of get on with the formula and do the practice questions, and it works, but perhaps it's not the most rewarding experience, right? So yes, there are some difficult classes, especially multi-stats and design experiments that are crazy hard. Yeah, that's true. That's true. There multivariable statistics are you need to know your linear algebra very well, and design experiments. Design experiment. Assume you're talking about design experiment with the ANOVA stuff, analysis of variance perhaps, or sample surveying. Yeah, so that's very classic stats. Classic stats. Multivariate statistics is not easy. Um, any intro probability book you would recommend? Any intro probability? Actually, I do, and it's free, and it's completely free. So let me try to find it. Which one right here? Do we have the what's the professor from U of T? I forgot. University of Toronto I was talking about. Michael Evans, right? Michael Evans, U of T. Books, probability book. And it's fairly comprehensive. Yeah, yeah, it's this one right here. It's one book and it's quite big, but it covers a respectable amount of material. Probability and statistics, the science of uncertainty. This is intro to SAT. No measure theory, okay? Lots of examples, lots of exercises. It's a complete package. And I strongly recommend. Evans is a big name in the field of stat, and I strongly recommend the second author's work as well. He has very intuitive, sorry, I would say accessible, okay, accessible introductions to stochastic processes as well as measure theoretic probability. So it's a complete roadmap, okay. But if you're asking just about the intro to probability stuff, this is an excellent book. Okay, let's take a look. For example, I'm kind of doing a live book review video right now. Hang on, where's OBS? Thank you. Any prerequisite? Well, I guess it's just basic. You can do this if you know Calc 2 and take Calc 3 concurrently. How about that? I think that's a fair assessment. So imagine if you know single variable calculus, you know how to take derivative, some basic integral techniques, you know how to um, you know how to work with power series, and that's about it. Okay, and perhaps some basic matrix stuff. Okay, you need to I mean, it's not a strict prerequisite. You need to know linear algebra to do this book, but things like knowing how to calculate 2 by 2 and 3 by 3 determinants help, obviously, and no prerequisites on real analysis whatsoever. Okay, you don't. This book is not about epsilon and delta. So Calc 3 is like sequence and series, right? No, not from North America. All right. So okay. So I'm by Calc 3 I refer to multivariable calculus. Multivariable calculus, partial derivatives. Okay, partial derivatives, multiple integrals. Yeah, basically that's what I was talking about. Okay, so it's recommended that you take Calc 3 concurrently while studying this book, because multivariable calculus is still not avoidable when it comes to intro probability, because you want to deal with joint distributions, right? Yeah, sequences and series was in Calc 2. That's kind of my experience as well. So sequence and series was included in Calc 2. That's true. And so yeah, let's take a look. For example, let's look at like a middle section, likelihood inference. What's likelihood inference? So you have the likelihood function, maximum likelihood estimation, inference based on the MLE, distribution free methods, and large sample behavior MLE advanced. So this is like the introductory mathematical statistics. Okay, introductory mathematical statistics. So probability and statistics are different subjects. They have not complete but still distinct objectives. Probability is a branch of mathematics on its own. It is kind of like geometry. It has its own set of axioms, okay? And you can think of probability more practically. You can think of probability as if we have a distribution, we want to derive characteristic of that distribution, and that makes sense. Okay, so in probability you have well-known distributions like the binomial, the normal, the gamma distributions. Right? In elementary probability, you deal with well-known distributions and you study their properties. But for statistics, the objective is reverse. You don't know the distribution. At least you don't know the full distribution. Maybe you know the form of the distribution, the class of the distribution, but you don't know the full details. Maybe you know the sample comes from a normal distribution, but you don't know the mean and variance. Right, so statistics start from the sample and you try to infer characteristics about the distribution. So these are reverse process. Right? And you cannot study statistics intelligently. Mathematical statistics intelligently, you can still do things like descriptive statistics without probability theory. But to do mathematical statistics, you have to know probability theory before. So that's why probability is usually a prerequisite for statistics. All right. So as I mentioned, this is very solid material, and it's written by well-respected researchers, and it's fairly pedagogical. Lots of examples. Okay. And do we have exercises? I think we do. There's also summary as well. Very student friendly. Exercises are here. Lots of exercises. And just by looking at them, okay, eyeballing them, they seem to have a nice progression from easier ones to harder ones. Okay, and I think this is a very good book. I mean, it's not like I mean, I used it. Didn't from back to back, but I used a good portion of it. Actually, I think this is more accessible to the one that I reviewed on the channel called Casella and Berger. So Casella and Berger was considered the gold standard. Is still considered the gold standard for a non-measure theoretic mathematical statistics. And this book, it has more details, which I think is nice for beginners. And it also has answers to odd numbered exercise. Oh my God. Oh, it's an answer, so it's not that crazy. It's not full solution. But it's better than nothing, right? Okay. So, yeah. Best intro to probability stuff. Best intro to probability book, in my opinion, and it's completely free. Um, I will. I tend to recommend resources that are free before. Why can't I go back? Okay. Anyway, this is silly. Chrome is being silly. But anyway, I tend to recommend free resources over paid ones, simply because I know how expensive books can be. There's that. So, and besides this, it's probably a good idea to learn some R programming along the way. I mean, you can use Python for sure. You can use Python. It's probably easier to find a job with Python. But nowadays, given all the AIs, I don't know how well that statement still holds. But anyway, at some point in your stat career, you will have to do like actual data fitting, data analysis, and simulations. So R helps a lot. Knowing R helps a lot, and it's quite intuitive to code with R. The codes in R are very similar to the formulas. So yeah, there's that. Um, any other questions you guys have about math? And yes, we use R a lot in stat. Of course, yeah. This is a basic skill in. I mean, it doesn't matter if you do applied or theoretical stats. You need to know some sort of programming stuff. So yeah, that's the book. And just because I was talking about the second author, Jeffrey Rosenthal, so go check out his books too. I mean, he doesn't have like a full. I was referring to some of his actual paperback books that you do have to pay for, but they're rather affordable books. A first look at stochastic processes. This is a fantastic book. The exercises, I wouldn't call them trivial, but they have a really nice progression. So this is, in my opinion, perhaps one of the most straightforward introduction to the field. Perhaps not as encyclopedic. Okay, this is after all, this is a first look. So I'm trying to say is compared to some of the more well-known books like the stochastic process by Ross, Sheldon Ross. This book is at a lower level, but it's a first look, and there's nothing wrong with that. Okay, and it's very straightforward. If you've never seen stochastic processes before, this is an excellent introduction. It covers things like the Markov chain, martingales, continuous process, including the Brownian motion, but no stochastic calculus here, just stochastic process. Okay, and it's not that thick. It's 197 pages, including the appendix. So it's a good bang for a buck. I don't know how much it costs right now. It's probably, oh, it's maybe ordered for $38 US dollars. But I mean, compared to mainstream textbooks, this is not bad, right? Yeah. So this is based on a 4th-year course, Stat 447 at the University of Toronto. So this one got my endorsement, okay. And another one, um, a first look at rigorous probability theory. This is perhaps once again um, the most accessible book to measure theoretic probability I've seen. This is written for people with very little background in real analysis, but still, once they get into grad school, they need to read like research papers and have to know the vocabularies at least of rigorous or measure theoretic probability theory. So once again, this book is very, I think, I think it's quite short. No, I think it's quite short. Yeah, it is quite short. It's barely over 200 pages, and it covers things like from the basics, the necessity and the need for measure theory, probability triples. That's the probability space, the Kolmogorov axioms. Further probabilistic foundations, expected values, inequality and convergence, distribution of random variables, stochastic process in gambling games, discrete Markov chain. So this is now treated in a measure theoretic framework. More probability theorems, right? So these you have the moment generating functions, weak convergence. So this is convergence in distribution. Now characteristic function, decomposition of probability laws. Now, this is actually pretty advanced. Conditional probability and conditional expectation. Yeah, very cool stuff. Martingales. This is rather short, I would say. You can use this as a companion to the stochastic calculus book, general stochastic processes. Here we have the Ito's lemma. Okay, I think the next, perhaps not. No, we can't do Ito's lemma in the next stochastic calculus video. Probably not. I think I have to say something about stochastic differential equations before I talk about Ito's lemma. So yeah, I want to talk about stochastic. So the idea, the most probable next episode in the stochastic calculus theory is on defining and interpreting stochastic differential equations. How about that? And then we can do Ito's lemma without measure theory. Okay. So yeah, this is the other book that I recommend. And guess what? It has an online solution manual. There's now a free public online solution manual to all even numbered exercises written by actual humans. Okay. Yeah. So, and you can see these 3 books that I just mentioned, the introductory level. This was the book I was talking about. This one, probability and stat, the science of uncertainty. Right. I think it's the same book, even though the cover looks a little bit different, but it's the same book. Perhaps that one was on Evans's website. Anyway, so this one is like level 1. Okay, the stochastic process book is level 2, and this is level 3, and they're all very accessible given the subject matter. Okay, given the subject matter, so these are all very accessible. Perhaps not the most encyclopedic and referenceable, but it's certainly good for beginners. I can say that for sure. I hope this is helpful because it's getting a little bit late, and I hope we had some fun with abstract linear algebra. We didn't read a whole lot. It's actually, I was I barely got through the second section today. I mean, we did one section last time. I barely got half, or barely went through. I mean, not. We're still actually in first section, vector space. Well, this is taking forever. Well, I mean, that's the idea of the live stream, right? I don't aim to cover everything in the book. The point is to do some math and have some chat, right? It's like almost like playing a video game, right? You're not speed running the whole thing. You're just enjoying the process. It'll be a good video to go over again. You mean the live stream? Wow, I'm very flattered. I always felt like my live stream are kind of rambling. You can maybe you can get something out of it in the process. I hope so. I really do hope so. But yeah, if you want to watch the recording, then certainly go ahead. I'm very flattered. Like if you find just me doing this stuff is valuable to you. Yeah, awesome, awesome. That's really great to know. Yeah, for some reason, yeah, I was really surprised because this is not super organized in any way. But my last live stream has gotten how many views already? 50K or something. Perhaps that's the where's my YouTube channel? I don't have my YouTube channel in my search tab. I don't know why. Anyway, I think the last one has gotten 55,000 views or something. That was crazy. And a lot of views were gained after the live stream is over, which was even more surprising. Though it's still out of my depth a little bit. I'm a bit rambling. I just studied data science for this really shaped my understanding more. Thank you so much. It is still out of my depth a little bit. And that's completely okay. I guess the idea is that I wish to share, I share enough information that connects what is the audience already familiar with, and perhaps some they perhaps don't know. Okay. Um, as I reply to one of the comments, I said an appropriate amount of math anxiety is a productive thing, right? Is enough to entice effort, but not enough to paralyze. So that would be a good balance to have, especially I mean there's no grade on the channel, right? So it is if you see something that you don't understand, it's probably a good thing, right? You don't have to worry about grades and stuff. Yeah. Anyway, it's getting a bit late and I'm really hungry right now. I know eating at this hour it's 10:30 and it's not good for and I gotta eat something. I just want to get this over with. But anyway, thank you guys for joining the stream. It's been a pleasure, and I really enjoyed it. I hope you guys learned something and had fun. Uh, that's the most important part. And I'll see you next time. Bye.